Heat. It's everywhere, right? We feel it every single day, but it's completely invisible. So how in the world do we measure it? How do you put a number on something you can't even see? Well, the science behind it is actually pretty cool, and it's happening all around us, all the time.
I mean, really think about this for a second. You grab a bag of chips, flip it over, and there it is, a precise number telling you exactly how much energy is inside. How? Are they just guessing? Nope. There's a very real method for figuring that out, and it all comes down to capturing that invisible energy.
The answer to that question has a great scientific name: calorimetry. At its heart, it's just the science of measuring heat flow. It's the tool that lets us turn that invisible energy into a solid number we can work with, whether we're talking about a chemical reaction or, yep, the calories in that bag of chips.
Okay, so to really get how calorimetry works, we first have to understand one simple, totally unbreakable rule about where heat energy decides to go.
The basic idea is something you already know intuitively. Picture this. You take a really hot piece of metal and drop it into a cup of cool water. What happens? The heat doesn't just disappear. It flows from the hotter object, the metal, to the cooler one, the water. The metal cools off, the water heats up, and this little energy exchange keeps happening until they both hit the exact same temperature. We call that point thermal equilibrium. And this right here, this is the golden rule. In a perfectly sealed-off system, energy is never lost, it just moves. The exact amount of heat the hot metal loses is the exact amount of heat the cool water gains. It's a perfect trade. This one simple concept is the foundation for, well, all of calorimetry.
Now, to talk about this properly, we use a couple of key terms. The system is the thing we're actually studying. So in our example, that's the hot metal. The surroundings is just everything else that's exchanging heat with it, the cool water. The whole game is just measuring how much heat moves between the two. So how do we actually measure this heat trade in a controlled way? We need a special gadget called a calorimeter. And believe me, they come in a few different shapes and sizes. On one end, you've got the coffee cup calorimeter. And yeah, it's often literally just two styrofoam cups, one inside the other. It's simple, perfect for classroom experiments. But, it's not perfectly insulated. But then, on the other end of the spectrum, you have the bomb calorimeter. This thing is a beast, a heavy-duty, sealed steel tank built for really high-energy reactions. When you need to be super precise, like when you're measuring the calories in food, this is the tool you use.
All right, we have the principle, we have the tools, so let's put them together and actually solve a little mystery. This is where calorimetry starts to feel like detective work. So here's the puzzle. Could we use everything we know about heat transfer to identify a totally unknown piece of metal? Oh yeah, absolutely. Here's how we'd crack the case. First, we heat up our mystery metal, drop it into the water in our calorimeter, and carefully measure how much the water's temperature changes. With that number, we can calculate exactly how much heat the water soaked up. Then we just apply our golden rule. The heat the water gained must equal the heat the metal lost. That lets us solve for the metal's unique thermal fingerprint, a property we call its specific heat.
And boom! After we run the numbers, we find out our mystery metal's specific heat is 0.38 joules per gram degree Celsius. We can look that up on a chart, and what do you know? It's a dead ringer for copper. Mystery solved. But this isn't just a neat lab trick. The same ideas, reactions that release heat, which we call exothermic, and reactions that absorb heat, called endothermic, are at work in products you probably have lying around your house. For example, have you ever cracked open one of those chemical hand warmers on a freezing cold day? That amazing, satisfying warmth you feel? That's just pure portable calorimetry in action.
So there are two main kinds, right? The reusable ones with that little metal disc inside. They're filled with a special solution, and when you click the disc, it triggers a chain reaction that releases a steady flow of heat. Then you have the disposable ones. Those are filled with iron powder, and when you open the package, oxygen rushes in and causes it to rust really, really fast, a process that gives off a ton of heat.
And of course, it works the other way too. Instant cold packs do the exact opposite. You break that little pouch inside, and the chemicals mix together in a reaction that actually needs to suck in energy to work, so it pulls heat from everything around it, including you, which is why it feels intensely cold.
So now let's bring it all the way back to that first question about food. The unit you see on nutrition labels, the calorie with a capital C, is actually a very specific unit of heat. It's technically a kilocalorie, and it's defined as the amount of energy it takes to raise the temperature of 1 kilogram of water by 1 degree Celsius. So how do they measure it? You already know the answer.
Scientists take a sample of food, put it inside a bomb calorimeter, burn it completely, and measure exactly how much the surrounding water heats up. That's how we know precisely how much energy is locked away in that food. By doing thousands and thousands of these experiments, scientists have figured out the average energy values for our food. Fats are by far the most energy-dense, giving us about 9 calories for every gram. Proteins and carbohydrates, on the other hand, both provide about 4 calories per gram.
Now, food companies don't burn every single thing they make, of course. Instead, they use a clever shortcut called the Atwater system. They analyze the food to figure out how many grams of fat, protein, and carbs are in it. Then, they just multiply by those standard numbers we just saw to get the total calories. It's a reliable system that's built on all that foundational data from calorimetry.
So at the end of the day, calorimetry is really just the science of tracking where energy goes. From hot metal to a hand warmer to the food you eat. It all comes down to that one question. Which leads to a final thought for you. The energy from the last thing you ate, where is it going inside your body right at this very moment?